Hi, welcome to series of lectures on electrical machines, and this video lecture is on transformers and induction motors. First, let's discuss transformers and then induction motors. So here are the contents of this video on transformers. Introduction. From this you will know what is a transformer and what are its applications, its principle of operation and its features and EMF equation. Next, construction. From this you will know the different types of transformers classified on the basis of core construction and their brief discussion, and from this topic you will know how to reduce the leakage flux. Next, equivalent circuit of transformer. From this you will know the importance of equivalent circuit of transformer, and you will also know the phase diagrams under different loading conditions. And from this topic you will know why the transformer is a constant core flux device. Next, losses and tests. From this you will know the different power losses in a transformer and why different tests are performed on the transformer, like open circuit test, short circuit test, and from this topic you will also know how to separate core losses. Next, efficiency. From this you will know the difference between power transformer and distribution transformer, and it will be also discussed about all-day efficiency and the rating of transformer. Next, voltage regulation. From this you will know what is voltage regulation and the conditions to obtain the minimum voltage regulation and maximum voltage regulation, and zero voltage regulation will also be discussed. Next, effect of non-linearities on the operation of transformer. This is the important concept which will tell you that what is the type of input that to be applied for a transformer for getting a pure sinusoidal output. Next, auto transformer. From this the important differences between single phase transformer and auto transformer will be discussed, and under what condition auto transformer is preferred to single phase transformer, and how to obtain auto transformer from a single phase transformer will also be discussed. Next, three phase transformers. This is the important topic of all these topics because the majority of transmission and distribution network consists of three phase transformers. So it is important to know about three phase transformers. So in this topic different phase groups of three phase transformers will be discussed, and it will be also discussed about open delta connection and the importance of Scott connection. Next, parallel operation of transformers. From this topic you will know the different conditions to be met by transformers for operating them in parallel. Next, Buchholz relay. From this topic you will know what is Buchholz relay and for what purpose it is used in transformer will be discussed. Now let's get into our discussion on introduction. Let's discuss what is a transformer. Transformer is a static device which is used for transforming AC electrical power of one circuit into AC electrical power of the same frequency in another circuit. Simply, transformer is a static device which is used for transforming AC electrical power of one circuit into AC electrical power of the same frequency in another circuit, and it can raise or lower the voltage levels but with corresponding decrease or increase in current levels. Let's analyze this statement. If suppose this is the one circuit and let us suppose this is the another circuit, and these circuits are magnetically coupled. There is no electrical connection between this circuit and this circuit, but these two are magnetically coupled. Let us suppose this is the AC electrical energy input given to this circuit. Now according to this statement, transformer will transform this AC electrical energy input of this circuit into AC electrical energy of the same frequency in the another circuit. So this is what we call it as transformer, and the side of transformer at which source is applied is called primary winding of the transformer, and the side of transformer at which load is connected is called secondary winding of the transformer. And please keep in mind that along with the transformation of power from one circuit to another circuit, transformer can increase or decrease the voltage levels, but with corresponding decrease or increase in current levels. Means if suppose the transformation of power from one circuit to another circuit is accomplished along with decrease in voltage levels, it can also be said that the transformation of power from one circuit to another circuit is accomplished along with increase in current levels. Simply, if primary winding is at higher voltage level and secondary winding is at lower voltage level, then according to this statement, primary winding will be at lower current level and secondary winding will be at higher current level. Now let's see the applications of transformer. The main important application of transformer is in power systems. If suppose this is the power station at which electrical power is being generated, and that generated electrical energy is being transmitted and distributed through transmission lines and distribution lines to the consumer terminals, and consumer terminals may be industrial loads or domestic loads or commercial loads, etc. The generated electrical energy is of levels 11 kV or 22 kV or 66 kV, but for transmission purpose the voltage levels are at hundreds of kilovolts. So in order to transmit that generated electrical energy at higher voltage levels, here it requires a transformer, which is step up transformer, which will step up the voltage levels. And similarly, at consumer terminals the voltage levels required are very less, that is it can be 11 kV or 440 volts or 220 volts or etc. So as transmission and distribution voltage levels are at higher levels, for consumer purpose those levels must be reduced to the required levels. For that, here a step down transformer is required. Therefore, power system now can be represented like this. Let us suppose this is the power station, and then this is the step up transformer, and this is the transmission line, and this is the distribution line, and now this is the step down transformer, and this is the consumer terminal. From the protection point of view, transformer can also be used as electrical isolator. That is, here this is the transformer primary winding, this is the transformer secondary winding, and these two windings are magnetically coupled. There is no electrical connection between this circuit and this circuit. Therefore, transformer also provides electrical isolation. And what is the importance of electrical isolation means? Let us suppose there is a huge fault here, and this fault, because of the electrical isolation, will not travel to the generating stations, because here coil which will behave like an inductor which will not allow sudden change, therefore fault will not travel to the generating station. So here generating stations equipment are protected because of electrical isolation, that is due to transformer. Next, the other important application of transformer are for electrical measurements. If suppose there is a necessity for measuring the line voltage here, as we know that these voltage levels are at higher levels which can't be measured by our normal 500 volts 100 volts measuring meters. So in order to measure those higher voltage levels, potential transformer is used. This potential transformer is connected to the line which is at higher voltage levels, and this will convert into lower voltage levels which is sufficient for the low voltage range measuring instrument. And similarly for measuring line currents which are at higher current levels with the low range ammeter, CT, that is current transformer, will provide the necessary or sufficient current which is required for the low range ammeter. And after obtaining the reading from the low range meters and by multiplying with suitable transformation ratio constant, then you can know the actual higher voltage levels or current levels values. And other Application of transformer is in electronics, where here transformer voltage levels and current levels are very low. Now let's discuss the operating principle of transformer, which is mutual inductance. According to Faraday's law of electromagnetic induction principle. If suppose this is the transformer core, which is a ferromagnetic material, or it can be ferrimatic material too, and let us suppose this is the primary winding which is wound on the limbs of transformer. Okay, this is first limb and this is the second limb of transformer. If we connect source on this side, this winding is called primary winding of transformer, and if load is connected on this side, then this winding is called secondary winding of transformer. Now let's recall what is a transformer. Transformer is a static device which is used for transforming AC electrical power of one circuit into AC electrical power of the same frequency in another circuit. So this is one circuit and this is another circuit which are magnetically coupled. That is, these two circuits are under mutual inductance. Then AC electrical power from one circuit is transformed into AC electrical power of same frequency in another circuit by transformer. And remember the statement that it can increase or decrease voltage levels with corresponding decrease or increase in current levels. If suppose this is the primary winding which is having more number of turns when compared with the secondary winding, then obviously the secondary induced voltage will be lesser than the primary induced voltage. So is why this type of transformer is called as step down transformer, or simply you can say that if N2 is less than N1, then that type of transformer can be called as step down transformer. So schematically it can be represented like this: primary winding turns more and secondary winding turns less, and these two vertical line represents the transformer core, which is a ferromagnetic material, or it can be ferrimatic material. And similarly, if secondary number of turns are more than the primary number of turns, then that type of transformer is called as step up transformer, because the secondary induced EMF is more than the primary induced EMF, and it is represented with LV, and high voltage side can be represented with HV. Now let's analyze the operation of transformer, that is, let's know how the EMFs are induced in primary winding and secondary winding. For that, it is necessary to know about Faraday's law of electromagnetic induction, according to which for the EMF to induce, either there must be relative space variation or there must be relative time variation. In case of relative space variation, conductor is in moving state and magnetic field is stationary. And similarly, for relative time variation, conductor is stationary and magnetic field is time varying. For the EMF to induce, the basic elements required are magnetic field and conductor. So Faraday's first law, which will tell you that when a moving conductor cuts a steady magnetic field, then EMF is induced in that conductor. So from Faraday's first law, conductor is in moving state and magnetic field is stationary. So this is the case of Faraday's first law, means here relative space variation, and the EMF induced under this case is called dynamic EMF because conductor is in moving state. And the examples for this case are DC generator. And similarly, Faraday's second law, this gives the EMF equation E is equal to N d phi by dt. So in this case, flux is time varying and conductor is stationary. So relative time variation comes under this case. And the examples for this case are alternators, transformers, because here conductor is stationary and flux is time varying. So now let's analyze the operation of transformer. When AC electrical energy input of frequency F is given to the primary winding of transformer, as this is closed circuit, so current will flow. Let that current be I, and we know that when current flows in a conductor, then magnetic field is set up in the form of closed loops. So now there is a magnetic field, and which is time varying because alternating current supply we have given here. So time varying flux, and this is the stationary conductor, and according to Faraday's second law, EMF will be induced in this conductor. So let that induced EMF be E1, and let the supply voltage be V, and now flux will take the path of magnetic core. Let that flux be phi 1, and this is the time varying flux, and now this time varying flux will cut the secondary winding. So here there will be an induced EMF according to Faraday's second law. Let that induced EMF be E2. Let the terminal voltage be V2. So now because of transformer, this AC electrical energy input is transformed from this circuit to this circuit without change in frequency, and the EMF induced in primary winding is self-induced EMF because the EMF induced is because of its own current. So now primary induced EMF in terms of inductance can be represented like this: L1 di by dt. Let the primary current be I1, so here di1 by dt. And the secondary induced EMF E2 can be represented like this: E2 is equal to M into di1 by dt, because these two circuits are under mutual inductance, and the EMF induced is because of the primary winding current. So is why E2 is equal to M di1 by dt, and this EMF is mutual induced EMF. So is why the principle of operation of transformer is mutual inductance, because this circuit AC electrical power is transformed into AC electrical power of same frequency in another circuit, and which is because of mutual inductance. So is why the operating principle of transformer is mutual inductance, and which is according to Faraday's law of electromagnetic induction. This is step down transformer schematic diagram representation, and similarly step up transformer diagram can be represented schematically like this. And to represent three-phase transformer, simply draw extra vertical line which represents the three-phase transformer core. Now let's discuss the features of transformer. First, transformer is a constant core flux device. Irrespective of load, the flux in the core is constant, and that you can understand from the operation of transformer on load. And second, transformer can be treated as constant power device. Earlier in the statement of what is transformer, I mentioned that transformer is a static device which is used for transforming AC electrical power of one circuit into AC electrical power of same frequency in another circuit, which means transformer transforms electrical power from one circuit to another circuit without changing frequency. So in that case only frequency is constant, but here I mentioned that it is a constant power device. Why? Because transformer is the most efficient machine which can have 99% of efficiency, and most of the transformers will have 90 to 99% of efficiency depending on their load and power factors. As the efficiency is very high, it can be treated as constant power device. And the other feature is transformer is energy conversion device internally. We shouldn't call transformer is a energy conversion device externally, because in transformer AC electrical power of primary winding is converted into magnetic energy in magnetic core, and then that is converted into AC electrical energy in secondary winding. So in transformer, as there is internal energy conversion, so is where transformer is a energy conversion device internally, but externally we shouldn't call it as energy conversion device. And the other important feature is it provides 180 degrees phase displacement. That is, the phase difference between the secondary induced EMF and primary voltage is 180 degrees. That is, E2 and V1 is 180 degrees. That is, the phase displacement between output voltage and input voltage is 180 degrees. And the other important feature is it is a negative feedback circuit, and this point you can understand from the operation of transformer on load, and I will tell you in short about this. That is, let us suppose this is the input signal, let this be the system, and let this be the output. And if suppose the output signal is fed back to the input, and if this feedback signal is decreasing the input, then that type of circuit is called negative feedback circuit. If the output signal aids the input signal, then that circuit can be called as positive feedback circuit. And in case of transformer, if this is the input flux phi1, and because of the flux phi1 linking with secondary winding of transformer, EMF is induced in secondary winding of transformer, and if load is connected, then current will flow in the secondary winding of transformer, and because of which flux phi2 will be created, and this flux phi2 will be fed back to the primary winding of transformer, and which will oppose the main flux. So is why transformer can be called as negative feedback circuit, and this you can clearly understand from the operation of transformer on load. Now let's derive the equation for transformer EMF. For that, if suppose this is the transformer core, and these two represents the transformer limbs, and these two represents the transformer yoke, and let this be the primary winding which to be wound on the limb of this transformer. But please keep in mind that there will be insulation present between the transformer winding and transformer core. Let the insulation be this one, on which the transformer primary winding and transformer secondary winding are wound like this, and this is the input supply given to the primary winding, and let us suppose the secondary winding is left open circuited, that is under no load. Therefore, as no load is connected, the primary current is called as no load current, and because of which here EMF E1 is induced, and let this flux in the core be phi1, and the EMF induced because of this flux in secondary winding be E2. So now the flux is of sinusoidal nature. Let this be the maximum flux phi m, and the time period be t, and if you observe here, flux phi changes from minimum to maximum in t by 4 seconds, that is equal to 1 by 4 fh. Therefore, average rate of change of flux is equal to maximum flux phi m by 1 by 4F, where maximum flux phi m is equal to flux density into cross section of the core. Therefore, that is equal to phi m into 4F, that is equal to 4 phi m into F Webers. Therefore, as this is the average rate of change of flux, in order to get the RMS value, we need to multiply this average value with form factor. Therefore, RMS value of EMF per turn is equal to 1.11 into 4 phi m into F, that is equal to 4.44 phi m into F. Therefore, as this is the EMF per turn, then the EMF induced in primary winding, which is consisting of N1 turns, implies E1 is equal to N1 into 4.44 phi m into F, that is equal to 4.44 N1 into phi m into F. Similarly, E2 is equal to 4.44 phi m into N2 into F. If you observe these two equations, phi m is same because core flux is same in transformer core. And if you divide E2 by E1, which will give you N2 by N1. This is represented with K, where K is called transformation ratio constant. This is the one of the important relation, but the thing you must note from this EMF equation is not this. That is, EMF is directly proportional to the phi into F, which implies flux phi is directly proportional to E by F. As induced EMF is directly proportional to input voltage, you can take phi is directly proportional to V by F. This is the important relation which you must note from the EMF equation of transformer. Why means if frequency decreases, flux will increase. If flux will increase, then there is a chance of magnetic saturation of the core. If the magnetic saturation happens, transformer will drag more magnetizing current from the input. If more magnetizing current, then power factor will decrease. How it will decrease means, now let's analyze that. Let us consider ideal transformer. In this case, if you observe, primary winding is of inductive nature, therefore no load, primary current and flux will be in exactly 90 degrees lagging with input voltage. And this is the case if we assume permeability is constant. But with excitation, permeability will change. Therefore, in case of normal transformer, V and flux will be like this and I0 will be like this. Therefore, I0 will have two components. One along the flux, which is called magnetizing component of no load current, and the other current which is drawn along the input voltage is called IC, which is core loss component of no load current, and let the initial power factor angle be phi naught. Now let us suppose frequency is decreased. If frequency decreased, flux will increase. If flux will increase, transformer will drag more magnetizing current. So if this is the initial magnetizing current, now let us suppose the magnetizing current is increased to this value. Therefore, now the resultant will be like this. And if you observe now, phi naught angle is increased. If phi naught is increased, power factor will decrease. Therefore, we must protect the transformer from getting into saturation. For that, the solution is, if there is decrease in frequency, we need to maintain V by F ratio constant. If we can maintain V by F ratio constant, phi will be constant. Therefore, transformer core will not enter into saturation. So, to make V by F constant with change in frequency, we need to change the input voltage. Therefore, if there is decrease in frequency, we must increase voltage. By that, we can make the V by F ratio constant, and by that we can make the flux constant, so that we can save the transformer from entering into saturation. And initial power factor angle will be around 60 degrees to 70 degrees. That implies initial power factor will be around 0.2. This is what you must note from the EMF equation of transformer. Thank you for watching, and if you like this video and my presentation, please like this video, share this video, and do subscribe to my channel. Thank you. See you in next lecture.